a set of PowerPoint on the testing of GR with the ngEHT. So this looks like a set of very exciting talks. We've got 6 talks in 1 hour. My name is Ziri Younsi, and I'll be moderating today's session. And our first speaker today is Misba Afrin from Jamia Millia Islamia. And we'll be talking about constraining black holes in Hordensky theory with EHT observations of M87 star. So without further ado, I see that you're on the call. So Misba, would you, the floor's over to you. Would you like to share screen and get started?
Okay,
And I will
Sandra would be running my pre-recorded talk because I'm having a very unstable internet connection. So over to Sandra.
Okay, sure.
Yes,
If I may, I'm sorry, Sandra, just one moment. I'll be giving, so I'm expecting around 8 minutes with 2 minutes for questions. It's okay to overrun slightly. At 8 minutes, I will sound a buzzer, which will sound like this. And that's telling you that that it's pretty much 8 minutes and it's time to wrap up if you haven't already. So with that, please, over to you. Thank you.
Okay, Sandra, if you can please run. Yeah. Thank you. Hello and lovely evening to all present today for the ngEHT meeting. I am Misba Afrin, a PhD student at Jamia Millia Islamia University in New Delhi. Today I'll be speaking about constraining black holes in Hordensky theory with the Event Horizon Telescope observations of M87 black hole. So, before starting, I would like to give a brief overview about how really the scalar tensor theories come into the picture of modifying gravity. So, the challenge of explaining a late-time accelerated expansion of our universe remains in GR. While the cosmological constant may have come to the rescue as a vacuum energy, its observed value is inexplicably small to theory. Thus, it has been suggested that a modification of gravity at cosmological scales may be responsible for the above effects, and in this line, various scalar fields have been used to model dark energy as well as dark matter. This is really how the scalars come into the picture of modifying gravity, and the most general scalar tensor theories have been shown to contain enough freedom to recover the cosmological background expansion as well as the large-scale structure of the lambda CDM without any need of the cosmological constant to explain the cosmic acceleration, while remaining theoretically consistent. So among the various available scalar tensor theories, the Hordensky theory is particularly exciting, and it describes the most general four-dimensional local Lorentz covariant scalar tensor theory with the Euler-Lagrangian equations containing at most second-order derivatives of the scalar and tensor fields. So this is really a very brief overview, and for an in-depth further reading in both the scalar tensor theories, the no-scalar hair theorem, as well as the Hordensky gravity, one might refer to these two wonderful papers. The last one is a review article. And for today's talk, my focus would be on the rotating black holes in Hordensky gravity, which have been obtained considering the action of a quartic Hordensky gravity. Please note the Q3 and Q4. These are generic functions of the kinetic term of the scalar field phi. And since there is up till a fourth order term, this is related to the quartic Hordensky gravity. In the Hordensky gravity, a no-hair theorem has been defined, and lifting the conditions of the no-hair theorem, one might obtain hairy solutions. So for the present study, we'll be lifting two of the conditions, namely the finite norm of the neither current right down to the horizon and the presence of a canonical term in the action. So lifting these two conditions, a spherically symmetric hairy solution has been obtained in the Horndeski theory, and more details about the solution can be found in these two papers. Subsequently, the rotating version of the spherically symmetric hairy solution has been obtained, and this would be the particular focus of my talk today. So please note that apart from the mass and the spin parameter, there is an additional hair parameter h, which has been shown to be uh, connected to these generic functions of the kinetic term. And using this metric, we'll be trying to constrain the Horndeski theory, for which I'll be using two of the uh, bounds on the shadow observables uh, uh, obtained in the 2019 EHT papers for the M87 black hole, and the first of which is the circularity deviation, which is found to be less than 10%, and hence considering the M87 as a rotating Horndeski black hole and with a mass and distance from Earth without any error bars, we have obtained the circularity deviation and seen that it is satisfied for the entire parameter space of the Horndeski black holes for both 90-degree as well as 17-degree observation angles. But more interestingly, the angular diameter bound at the current resolution of the EHT puts a strong upper bounds on both the spin parameter as well as the negative value of the hair parameter, and only in a very small portion of uh, the parameter space, the M87 black hole can have a Horndeski background. So we are now interested to check whether within this accordant parameter space, the shadows in the Horndeski theory can be differentiated from those in GR, and namely those of the Kerr shadows. So please note that these white regions have been excluded from calculation as they correspond to naked singularities, and we carry out a systematic bias analysis in the bounded parameter region obtained from the previous slide, and taking the Horndeski black hole as a model and the Kerr spin as an injection, we calculate the reduced chi-square between the model and the injection using two shadow observables, the area and the oblateness. And please note that over here we can increase this n and thus include more shadow observables, which would really be interesting. Over here, the standard deviation is kept at the current resolution of the EHT, and I'll reiterate that the whole bias analysis is carried out within the parameter space in which the angular diameter is consistent uh, for the Horndeski gravity. So we can see that around the a very small region centered at the injected spin, the chi-square is less than 1, and the shadows in the two theories are not distinguishable. But interestingly, outside for a much larger region, the shadows in the two theories are distinguishable. So this is true for both low as well as high values of injected spins. And finally, we have found the best fitting spin parameter as well as the corresponding minimized chi-square of the Horndeski model for various injections of the Kerr spin. So quickly concluding, with better resolution of the ngEHT observations, one can put tighter bounds on the Horndersky gravity and at the same time improve the distinguishability of the shadows in the two theories, that is the Horndersky and Einstein's GR. So I'll thank you all and take questions if any.
Thank you, Misba, for the very nice talk. We have time for one or two questions. If you do have questions, please raise your hand. I'll let you in. And if there isn't time beyond this, then please feel free to put your questions in the chat window below, or of course on the Slack channel, day 5 breakout testing GR. So are there any questions? I see a hand raised there by Alexander. Please go ahead, Alexander.
Okay. You quoted Babichev et al. Paper, but in this paper, he reproduced Reissner-Nordström metric, but with additional charge. So due to coupling scalar tensor theory. In this case, metric looks like Reissner-Nordström, but charge is not non-electric one. So in this case, what about your comment about this issue?
Well, as I have quoted the papers, I'll just share my screen. Just a moment. Yeah. So
yes,
over
yes,
here,
this one.
yes, yeah. The spherical symmetric solution has been obtained in this paper actually. So, but over here, the authors have not explicitly said anything about the hair and whether it's a primary one, secondary one. But as far as my analysis goes, it is a secondary hair, but of course without a Gaussian charge.
Okay, well, thank you very much, Misba. Thank you, Alexander, for your question. It's time to move on, and our next talk will be given by Alexander, who's just joined us. Thank you. So Alexander is from the ITEP in Moscow, and will be talking to us today about constraints on a tidal charge of the supermassive black hole in M87 star with the EHT observations in April 2017. So thank you very much, Alexander. Over to you, and I'll make a little beep at around 8 minutes.
Okay, thank you. It's first of all, I would like to thank organizer for this nice opportunity to be here and to present this talk, because it's around this image, famous image, but also it's based on synchrotron emission, let us say VLBI technique, and also GR loss around in strong gravitational field around near black hole. That is one of the first book about synchrotron emission, but it was rediscovered in 40s. And these two persons, Ginsburg and Shklovsky, used synchrotron emission as a key role in many astrophysical objects, including Crab Nebula, etc. And also VLBI technique was introduced in Soviet Union and the United States. It was international experiment in this direction. That is logo, that is references. What about shadow? So one of the first paper was published by Lumine, but also 20 years ago, Falke and Melia-Gol considered formation of shadow in different spectral bands. Here you see in millimeter band and centimeter bands. So in this case, people 20 years ago, they expected that it will be possible to detect shadow in the millimeter bands, but also I borrowed this slide from Melia website, and as we show later, so in this case, it's correspond to case when observer is in equatorial plane and spin is very close to 1, y. And also it was motivated by Radiative mission. It was launched in 2011. It flew for 8 years, but angular resolution at 1.3 centimeter was around 7 microarc second. In this case, it was a hope that is to reach event horizon, but real event horizon, but it was not possible due to scattering. And also we proposed to test general relativity with shape and size of black hole shadows. We published article, and also it was connected with Chandrasekhar book, because it's you see in Chandrasekhar book you could see this critical parameters of two parameters for geodesics. It separates scatter and capture. But also Chandrasekhar reproduced this picture. Practically, it's a shadow for extreme spin parameters, but it was also early published by Bardeen. But also this issue was considered in my old paper, published 35 years ago. It was, let us say, critical parameters for a shadow which separates scatter and capture. And Chandrasekhar knew this paper, and also he wrote about this. And also you see it's also separation of critical parameters, shadow and scattering. So that is Schwarzschild case. It's purely parabolic curve, but here you see it's extreme cap parameter, spin parameter is 27. So, but if our observer is located in equatorial plane, you see that is solid line corresponds to extremely rotating black holes, and dotted line corresponds to Schwarzschild case. It's well known in textbook. But it's important to know that maximal parameters or in the vertical direction as a function of spin is 2a. So in this case, if people could reconstruct the shadow, it's possible to evaluate size, not size, spin. So it's for polar axis, it's for intermediate parameter, spin parameter, that is for extreme spin parameter for different position angle of observers. And we suggested that in our paper 16 years ago, we suggested that it may be detected with VLBI technique with probably millimetron or sub-millimetron, as it was expected. And also important thing that if we consider Reissner-Nordström metric, electric charge or non-electric charge, important thing, the Reissner-Nordström case. In this case, we could derive analytical expression of size of shadow as a function of charge. Here you see solid line corresponds to Schwarzschild case. For extreme rotating black hole is radius of shadow is 4m in m units. So, but if people also suggested to consider tidal charge, Reissner-Nordström is tidal charge. In this case, Q squared may be negative. It's negative charge may be signature of Reissner-Nordström of let us say tidal charge may be signature of extra dimensions, Randall-Sondrum theory, or it may be also signature of Hardetsky theory, as it was shown in Babichev et al. Paper. But also there are analytical expressions, size of shadow is a function of charge. And also since people, Ben Noon and others suggested to use, let us say, tidal charge in Sagittarius A, in this case, even in 2008, it was constrained on size of spot shadow. In Sagittarius A, it's possible to evaluate to constrain charge, as it was done. So, but also wrong pictures of black holes. I would like to show you here that it's not possible to hide size part of accretion disk behind a black hole. It's always visible. But in spite of that, people use these pictures very often. But here you see also famous Kip Thorne and co-author paper. Here you see shadow near the black hole. So I will skip these details, but also event horizon telescope data. But also here, again, I reproduce this picture for Reissner-Nordström metric. But recently, event horizon telescope team published constraint on parameters of black hole, like charge. They call it like charge. And here you see that is Reissner-Nordström metric. And here you see a size of shadow is a 4m, as it was done early in our paper, but also it was from press release. And also if we consider tidal charge, that is constraint on tidal charge, is Q squared is negative, constraint on tidal charge from the event horizon telescope data, if you analyze this data in the same manner as it was done by Kacher, Lakota and others, so tidal charge Q should be more than minus 1.22. So, and also few words about, let us say, alternative for galactic black holes. For instance, people suggested to use dark matter concentration. It was dispute about this issue, but important thing that instead of supermassive black holes, people suggested dark matter concentrations with constant density. In this case, there are only two possible potential when there are elliptical curves of trajectories. It's, let us say, harmonic oscillator potential, Newtonian one. If we consider these two cases, we could say, as it was analyzed in my paper recently, so this data for, let us say, balls with constant density, dark matter, are not consistent with observations. That is observational data for bright stars, but for harmonic oscillator potential, center of ellipses should coincide with center of force. So concluding, so consideration of alternative supermassive black holes are not reasonable, is reasonable, but RAR model, which was suggested by Ruffini and Quarters, shadows do not exist. For instance, in F87 or in Sagittarius A. Thank you very much. It's 10 minutes exactly. Thank you.
Thank you very much, Alexander. It was a lovely talk and wonderful to see a nice pedagogical review of these matters as well. So thank you for that.
Thank you.
We have time for one or two quick questions. Okay, well, if there aren't any questions, I have a quick question, Alexander. So could you please remind me, when was this first paper, this millimetron experiment, when did this white paper that proposed measuring the shadow come out?
So it's also a very interesting story because its preparation study is very long. And now, even at the beginning of this year, it was approved like perspective, let us say, mission for Russian Space Agency. But now they withdraw their decision. So, but important thing that position of this, let us say, satellite, it has to be a cryogenic detector with, let us say, frequency even less than 1.3 millimeter, but position has to be L2. So 3 million kilometers. So it's in this case, angular resolution has to be 10 to the minus 9. So excellent angular resolution. So, but its perspectives are unknown at this stage. But ideas about millimetron were introduced, I think, more than 30 years ago, after radioastron. Because radioastron, again, I'm repeating that radioastron has excellent angular resolution, 7 microarc second. But unfortunately, wavelength was too long to detect some kind of relativistic signatures like shadows.
I see. Well, thank you very much, Alexander.
Thank you. Thank you.
Thank you again. So moving on, our next speaker today is Saurabh. Thank you for the phonetic spelling, by the way. And Saurabh is from the PDPIAS at Charles University, and will be speaking to us today about the investigation of deviation from GR in semi-analytic reacts. So the floor is yours, Saurabh. Go ahead.
Yeah, thanks, Ziri. I'll just quickly share my screen. Yeah, I hope my screen is visible. All right, hello everyone. My name is Saurabh, and I'm a master's student at the Imperial Institute of Advanced Sciences, Applied Sciences at Charles University, India. So the current topic for today's talk is investigation of deviation from general relativity in semi-analytic. So this work is being done with Yusuke Mizuno and Prashant Koshirakuta, and I'll further begin. So the basic roadmap of testing GR is first taking a generalized solution which would encapsulate Kerr paradigm, which when other deformation parameters put to 0, it just gives us back the Kerr metric, and then we simulate and make some predictions regarding that particular observable, and then we compare our simulations with the data sets. And then we try to find if there are some possible deviation from general relativity or not. So this is a basic roadmap when we're trying to test GR in any particular set of observables. So here we are particularly focusing on just some preliminary results that we have found using RIFE modeling in a particular axisymmetric and parameterized solution. So here we are focusing on specifically on KRZ spacetime, which looks like a bit complicated here. And this is a set of spacetime where a more generalized solution is given by this particular equation. And here we are particularly focusing on a static case where we have taken spin to be 0. And the choice of parameters are just 2 parameters, which is A01 and W01. So here, if we add up more number of parameters, as we can see by W1K function, we can have infinite number of parameters. But as for this particular study, we are just focusing on A01 and W01. So in previous studies, we have also studied as to how this particular space-time can actually present to a novel test for GR using particular observables, which is size and shape, for which the references here. Interested people can go and study. So here where we have found that some particular constraints can be good, but still it's a bit of question that whether these constraints are how better these constraints and how robustly we can actually constrain them using just these 2 observables, which are size and shape. So here we are trying to model our space-time with RIFE modeling, which is radiatively inefficient accretion flow. So for this purpose, we wrote a code for which is GRRT squared, and there are two steps in this whole process, which is Raytracing and solving radiative transfer equation. So for Raytracing, there are different methods which can be employed in order to solve geodesic equations. So either we actually solve the first order differential equations, which is separating the second order differential equation of radial and angular part, and getting a list of, let's say, 6 to 8 differential equations, and then solve them subsequently, or just apply a fully numerical approach and then just solve the second order geodesic equation. So in our GRRT code, we have employed both these aspects, but for our initial results, what we have found is the first order ODEs gives us a much more computational advantage, which is solving them very efficiently and utilizing less time. So for that purpose, we use first order ODEs. And for solving radiative transfer equation, we used a formalism where the radiative transfer equation can be decoupled into 2 differential equations, which can be seen here in terms of optical depth and intensity. So the amazing part of this GRRT code at the moment is this is actually generalized for arbitrary static spacetimes, in which we just have to give metric components for that particular spacetime static, and it will give out the modeled the particular accretion model in which we want. So these are some of the salient features of the code, and it is currently under development. It is purely written in C++. So if in order to check our results with the previous results which have already been found as a sort of calibration, so we have implemented some few test models as of spherical accretion, some analytic models, and thin accretion disk as to see if they are matching up with previous results or not. And another advantage of this particular code is that we can easily add new models and new space-time. So there's no much hustling in addition of any new feature to this particular framework. So, for our current purpose, for our current work in the semi-analytic RIFEs, we have taken some particular consideration as to what sort of space-time we want to have, and what sort of what sort of other capabilities this code have. So these are the list of current implementations. I will get back at the end if I have some time at the top. So for the moment, I'll skip the slide. And the current assumptions, and kind of apologies for what's happening in the background. It's festival season, so really can't help it. But for the plasma model, what we have assumed is the accretion flow is happening described by thermal distribution. The electron distribution function is taken from the fitted formulas from Pandya et al. The accretion flow is a Keplerian accretion flow around the outside the ISCO radius, and within the ISCO radius is pure free fall state. The magnetic field, there are different magnetic field configurations which one can take. For this work, we have taken toroidal and radial magnetic field configurations. Normalization factors, which is electron number density and temperature. These are varied according to M87 results and keeping the total flux to 0.5 Janskys. The disk height is thought to be thin disk in terms of H over R. So that as we take it to 0.1, and the observing frequency is 230 gigahertz. So the overall model for this RIF model consists of lots of number of parameters, which can be inclination, field of view, the deformation parameter, these normalizations, and whatever accretion flow, the magnetic field configuration, and the total number of pixels. So this seems to be a quite degenerate model in terms of we have more number of deformation parameters, but still it seems a worthwhile study to check how results actually look like. So for the starting, we've taken the accretion flow to be Keplerian all around, and we have found that in different with different values of deformation parameters, the size and the size and shadow structure are a bit different. So the size is different, but the shadow structure is not that different as it seems to be expected. But here we are focusing on static space-time, so it is spherically symmetric. So we really cannot assume, we really cannot expect much in terms of shadow structure. But here we can see that peak intensity and the size is definitely changed when taken the deformation parameters to 0.5, negative of 0.5 and 0.5. So when they are turned to 0, we get the pure soft-shell case, which can be seen here. So it can be seen that how the peak intensity is being different as compared to the other cases. And mind it, the field here is toroidal magnetic field all around. So this is the cross-sectional intensity of the previous figures. So here, just to draw some comparison between just these two particular images as to see if we can differentiate these two solutions. So here it can be seen that the peak intensity and this overall size is actually different as compared to other properties. The structure, the profile, it follows a similar profile. There is not much deviation, but here what it can be seen that maybe if we have a much more sophisticated simulations are also. I forgot to add one point that these simulations were performed with 200 cross 200 pixels. So in terms of resolution, it seems to be fine to bring out some features. Still much high resolution simulations are still needed to actually see some more features. So here we can see that that there can be some different subphoton rings in the structures of different with different peak intensities, and the overall size actually changes with different values of deformation parameters. So keeping the magnetic field to be radial, not much is seen here as well in terms of peak intensity and size as expected, and still this is just drawing a comparison between the two images. So it's actually quite important that when we are trying to simulate these space-time, there are a lot of different deformation parameters, and once we change the values of those deformation parameters, there's quite a possibility that we might get back the similar solution as of a different pair of values, thus adding more degeneracy to those parameters. So here we have seen that the overall model contains a lot of different parameters, right? So they can actually give back the original state as in terms of another image of same pair of different pair of values. So as in summary, what we can see is that we did arrive modeling and generalized parameterized space-time. In order to do so, there is a standalone GRRT code was prepared where we can add different kinds of models and generalize in terms of static spacetimes for GR testing, and it is in heavy upgradation as of now. And most of the simulations as of now, just as preliminary results, suggest that the change in size and peak intensity is what we can get in terms of deviation from the standard curve paradigm or standard swashing.
Sorry, Saurabh, we have to wrap up.
Yeah, so just wrapping up, these are points, and shadow structure can be changed in terms of if we have additional spin. So in terms of what's next, the study which warrants more study is the Fourier domain study, which is studying how the images will look like in Fourier domain, doing EHT and GHT imaging, and seeing if we are able to recover those solutions and effect of different electron distribution functions, as in terms of power law or kappa or hybrid EDFs, as to see if they change these things or not. So thank you so much.
Thank you very much, Saurabh, for the comprehensive talk. Very nice. We unfortunately don't have any time for questions, so if there are any questions, please put them in the chat or on the Slack channel. Let's move straight on. Our next speaker is Aaron Held. I've got you as Imperial College London, but I know you've recently moved. So where are you right now? There we go, perfect.
Yeah, so currently I'm still in Jena, although not in person right now, and I'll be moving to Princeton in a week.
Excellent.
Exactly. So I apologize in advance for the potential sound issues in the background.
That's no problem. It's a pleasure to have you, Aaron. Thanks for speaking today, and I hand the floor over to you. 8 minutes.
Yeah. Thanks a lot, Ziri. So I want to talk about generic image features of black holes, and in particular, I will apply a set of principles regarding regular and local black holes. And here on the right-hand side, you already see two images sort of as a preview. And of course, they're also obtained by ray tracing and radiative transfer of a disk model surrounding the geometry. And so just to, so this is combined work with Astrid Eichhorn, and I will also be reporting just very briefly on work with two of her students. So we already had a nice example from Saurabh regarding what I would say is a principled approach, where you start in a specific theory beyond GR, and you try to obtain a shadow image, and then you try to compare two shadow images, one from GR and one from beyond GR, to constrain the theory. And on the other hand, you could start in a parameterized approach, where you really parameterize all possible deviations from an axially symmetric and stationary spacetime. And of course, both of these approaches are valid, and I think both should be pursued. Both have their downsides. And Astrid and I, we think that there's a gap in between, sort of bridging between these two approaches, which we would then call the principled parameterized approach, where we try to find characteristic image features for a class, for a family of spacetimes that is based on fundamental principles. And if you want to hear more about that, I encourage you to go back to Astrid's talk, which she gave on Tuesday. I want to make 2 points here, and that's really just explaining the basic principles that we put in and how that affects the spacetime and thereby the images. And the second concerns circularity, which was also already mentioned by previous speakers. And in particular, these black holes that we get out of applying a locality principle are non-circular spacetimes. And I'll touch upon this in the last bit of my talk. So here you go, constructing these regular objects. You start out from Kerr spacetime, and you focus on the mass parameter. So there's a lot of other potential deviations that you could build on Kerr spacetime, but we focus on the mass because we're coming from quantum gravity. We know that an effective mass which decreases towards the center of the black hole and decreases to zero can actually remove singularities. And therefore, it's a generic mechanism of how to construct regular spacetimes. And so then we apply these 4 principles: regularity, so no curvature invariants are divergent any longer; a Newtonian limit, we would like to preserve that; simplicity, there's no additional physical scale, so there's just one new physics scale; and locality. Locality will be very important, and thereby I really mean that the new physics is tied to local curvature scales of Kerr spacetime. And you can combine these 3 first principles. You can think of that just regularity telling you that the mass has to go to 0, Newtonian limit telling you that the mass has to asymptotically approach a constant value, which we then call mass, and simplicity connecting the two such that the mass has to continuously and monotonously decrease towards the center. And that immediately tells you that the horizon of that black hole will also shrink. The black hole will become more compact, and therefore also the shadow will become more compact. Now, bringing locality into the game and starting on Kerr spacetime, there are different curvature invariants on Kerr spacetime. And what we do is we construct an enveloping invariant which envelopes the maximum of all the absolute values of these curvature invariants. And you can see that here in the form of an equation. And you can take that and you can then construct an explicit mass function, which of course depends on the angle now. And here you can see this angular dependence, and you see that in the equatorial plane, the curvature corrections are largest, and that does make sense. So the blue line here is the maximum of the curvature invariance, and the green-yellow contours are this approximation, so that fits quite nicely. And it does make sense that this is largest in the equatorial plane, because that's, of course, where the curvature in Kerr spacetime is the largest. And that affects the horizon structure. Now the horizon is not just shrunken, but it depends on the polar angle. So there's a profile of the horizon which makes it depend on where you are in terms of the equatorial plane. All right, and that leads to interesting image features. And here you see 3 of these images, now focusing just on the prograde side where the effects are the largest. And what you get in general from having a regular geometry is that I said the horizon shrinks and therefore also the shadow shrinks. You can appreciate that here. The interior of the shadow is on the right, and you see that the boundary moves towards the right in the regular spacetime, so the shadow is actually becoming more compact. And then photon rings, these are these bright lines here, 1 and 2, or here, they are actually stretched out. So you do see that this is a smaller deviation this here. And then it depends on the question whether the spacetime follows this locality principle or not. And here you see a spacetime which does, and here you see, here you see one which violates the locality principle, and here you see one which obeys the locality principle. And you do see that there's interesting additional features here, which are cusps in the shadow boundary. These are very prominent, and they might be interesting in terms of also dynamics. I want to highlight one thing, and that's that the n=1 and n=2 photon rings, they are really key to sort of constraining this physics, because these are where deviations will start. You see that there's a gap opening. So this is something that we're exploring more prominently now, also regarding degeneracy with a disk model. And then I want to mention circularity. So here you have the mathematical definition of circularity, but you can really think of it as inverting the 2 coordinates which correspond to the killing vectors. The psi1 and psi2 are the killing vectors of the axially symmetric and stationary spacetime. So if you invert time and spin of the black hole and the spacetime stays the same, then the spacetime is circular. And indeed, Kerr spacetime is circular. Actually, all vacuum solutions of GR are. But these black holes that we construct following this locality principle, they are no longer circular. And the interesting thing is that this is the reason, and we now understood this, why these constructed spacetimes are not captured by the used parameterizations in the literature. Because these are also all circular, which you can verify by explicitly plugging into these metrics here. And so one should be cautious in applying parameterizations. What are the actual ingredients that one puts in, and ask whether I should assume circularity or not for physics beyond GR. So to make this point once more, if you take a general parameterization with 10 free metric elements and you apply killing vectors so that the spacetime is axisymmetric and stationary, that does not necessarily reduce the number of free components. It just reduces that they all depend only on 2 coordinates. Then you can perform coordinate transformations, and barring potential different classes that you cannot connect by coordinate transformation, that takes you down to at least 6 free metric functions. So there's no way of reducing a general axisymmetric and stationary spacetime further. And then if you do apply circularity, which then doesn't capture some of the physics, I give another example here, then actually you can reduce to 5 free metric functions, where you see that all of the components that are not invariant under inversion of t and phi, they now vanish. And then you can apply further principles like hidden symmetry and further reduce the set of physics beyond GR. But these are assumptions that one makes, and one should be aware of that. That's why I highlight this point here. And so stay tuned for potential more on this question of circularity and generic parameterizations. And with that, I'd like to thank you for your attention.
Thank you very much, Aaron, for the great talk and for being right on time. So we have time for 1 or 2 questions. I see a few hands raised. I'm just going to go in order of what I've seen. So the first is Dimitri. Go ahead, Dimitri.
Thanks for the really interesting talk, Aaron. So I'm curious about the circularity condition and when you violate it. So there are solutions in GR that are non-circular, something like the gamma metric, for example, but it's unstable, right? So it should, if it existed in GR, it would emit gravitational waves and settle back down to something like Kerr. Do you know if these solutions would actually be stable?
So this does depend on the dynamics, since we sort of parameterize a large class of spacetimes for which we do not know the dynamics. In principle, it depends on, first of all, whether these spacetimes are solutions to some theory or which theory, and then in that theory, whether they are stable or not is a question we haven't addressed. But you could, in principle, address it for these scalar tensor theories here. But I also do want to mention that there are neutron star solutions in which the magnetic field is not circular. I think that's sort of where this notion, where this circularity, the name comes from, that the electromagnetic field is not circular. And then you can actually construct even neutron star solutions. This is here in this paper here, which are circular spacetimes in GR.
Yeah.
And non-circular spacetimes.
Yeah, thank you.
Okay, time for one very quick question from Cheyu. Please go ahead.
Yes, thank you very much for the nice talk. I just have a question about why can the circularity condition remove the R theta components of the metric? I think it's only restricted T5 flipping, right?
So there's a really nice review of this, because I mean the circularity condition has played a big role in proving uniqueness of the Kerr solution. So there's a nice review in a section of the Wald book on GR, where sort of the math papers are reviewed, and you can explicitly in terms of math see why you can remove these coefficients. But an intuitive way to understand it is that circularity means inverting t and inverting phi, and if you invert t and phi in these components, then you sort of they have to vanish to make the space-time be independent of that transformation.
Yeah, I just have a question on R theta component.
Yeah, but so why are you specifically concerned with the R theta component?
Yeah, I mean, if you just look at the metric, it doesn't depend on dt and d phi, something like this, no?
Oh, but so
I'm so sorry to interrupt.
Yeah, we can discuss it later.
Yeah, we
Let's
can take
discuss
this
this in the
offline.
chat. Yeah,
Yes, thanks.
Thank
No
you.
worries.
Thank
Thanks for
you
the question.
very much again, Aaron. Very nice talk. Thank you. So next speaker is Alexander Bonilla Rivera from UFJF. I can see you there. He will be talking about testing alternative theories to general relativity with EHT 2017 forecast and future perspectives. So 8 minutes. The floor is yours, Alexander, please.
Hi, everyone. Let me share my screen. Okay. And let me do one thing here. I changed a bit the title, but no problem. Well, thank you for invitation to this talk. I'm going to speak something about the modified gravity, gravitational waves, next generation on event horizon telescope. This is the outline, introduction and motivation, theoretical framework, gravitational waves in modified gravity, methodology and results, or preliminary results, and summary and conclusions. Okay. For example, from the nanograph program, we have the possibility to obtain information of low frequency gravitational waves. You know that we have the opportunity to live in the era of gravitational astronomy. And you have here the spectrum of gravitational waves from the high frequencies to the low frequencies. For example, ground-based interferometers how LIGO and Virgo work very good in high frequencies, but we have the possibility to go to low frequencies with a laser interferometer antenna in the space with LISA. And in this moment, we have a very nice work with the pulsars timing arrays. In principle, these gravitational waves they are of low frequency, and the source can be due, for example, by mergers of supermassive black holes, for example, or primordial gravitational waves, or phase transitions, many things. Okay. The gravitational waves detected by this project, nanographs or EPTAs, International Pulsar Timing Arrays, the detector are building how a galactic scale gravitational wave detector. We need to observe an ensemble of ultra-stable millisecond pulses to extract the correlated signal from the noise. Gravitational perturbations are correlated among different pulsars, and we can obtain information from this correlation, how you can see in the plot to left down side or in the screen. And here you can see the evolution of the merger. These mergers take many tiny billion of years, for example, in produce this merger. Different, for example, in a black hole, astrophysical black hole that can take seconds in produce the merger. But you can see, for example, you begin with the dynamical friction from the right to left. You can the black hole, supermassive black hole mergers can have, for example, jets of radiation, and after that you have the gravitational emission due to the merger, and after that you have one recoil of the two of the final hypermassive black hole, I think. But this dynamical evolution take many time. In principle, that you can detect with this technique is a continuous gravitational wave signal, no individual events. And with this signal, for example, you can see here different projects, how advanced LIGO, LISA, and nanographs, for example, to different epochs to the future, for example. But you have continuous emission that is due to a diverse population of mergers of black holes. In principle, you don't obtain information the one event, for example. But with this signal, we can prove, for example, we can do a test of the general relativity. This you can see here the strain of the gravitational waves produced by supermassive black hole population, and you need many information, astrophysical information about this system, how, for instance, galaxy max function, energy emitted per logarithmic frequency interval, and so on. And here you have the possibility to obtain information about the signal signal of to noise. And here you have the correlation function, for example. Through that, we have a gravitational spectrum, and you have a signal to noise ratio, for example, here. And with that, you can obtain information about the alternative models to general relativity through this expression that is knowledge how amplitude of the running of a Planck mass. The running of the Planck mass centers as the friction term, and it is responsible for modifying the amplitude of the tensor modes, acting as the damping term during cosmic time. And here I can show you the preliminary results. You can obtain this signal to noise ratio that in principle is possible to detect in this experiment, in these observations, these signals. But in principle here, we have a forecast with regard to different parameters that characterize the partures of general relativity. And we can show you that, for example, with the 12.5 years or 15 years of observations of pulsars timing arrays, you can obtain an improve or constrain these parameters.
I'm so sorry to interrupt, Alexander. We're out of time. Could you wrap up very quickly, please?
Okay.
Thank you.
And you have here different years of detection of pulsar timing arrays, and you can link these observations to other experiments how LISA and obtain information from one event, for example. But we need to do a merger with other experiments in astrophysics to obtain information, for example, from the electromagnetic sources. And the next generation event horizon is very important to obtain information to do this work and obtain information, for example, from the inflation. Thank you.
Thank you very much, Alexander. Unfortunately, we're out of time. We'll have to move straight on to the next speaker, but thank you. Our next speaker and our final speaker is Alex Lupsasca from Princeton, who will be talking about the conformal symmetry of the photon ring. Thanks very much for hanging on in there, Alex. The floor is yours.
Thank you. I have a very short amount of time, so I just want to make a much simpler point today. So we've seen the first image of M87, which is absolutely amazing and a great technological achievement. And the big question is, as our technology improves, what will we see next? And based on GRMHD simulations, we think that a sharper, higher resolution image would look something like this. And we've produced many such simulated images, and they all share this very striking feature that we see a very narrow, bright ring on top of the main emission, which has come to be known as the photon ring. And at first, this should be surprising. Why is it that as you vary the astrophysical conditions around the black hole, you always see this ring? And what we've come to understand in the past couple of years is that this ring is really a result of lensing by the black hole. And as a result of this lensing, whenever you look at an image of a black hole, you'll have some light rays that come directly to you, these so-called n=0 light rays that are weakly lensed and just show you an image of what's around the black hole. But on top of that, you can have light rays that do a U-turn around the black hole. So n=1 turns around the black hole before they reach you. And these give you an additional image of all the stuff around the black hole. But because they have to do this extra turn, they're lensed into a ring-like shape. And in principle, you can have light rays that go around multiple times. So they can do 2 turns. These are the n=2 rings, that n=2 light rays that are being shown here. And because it gets harder to push light rays into these orbits, the resulting image is lensed into an even narrower ring. And so when you look at the full image, you see the totality of these light rays, and that results in an image which consists of the background emission plus these rings on top that correspond to the images from orbiting light. So this structure has been confirmed in state-of-the-art simulations. So for instance, if you look at the image I showed you before, you take cross sections through the horizontal and vertical axis here. That's what we show here in blue and red. And when you zoom in on them, you can separate the contribution to the intensity into layers that correspond to photons that did a different number of orbits around the black hole. And in state-of-the-art simulations, we can see at least 3 photon rings on top of the image. And so the picture you should have in mind is that it's a completely universal, that is to say, matter-independent effective general relativity, that you look at a black hole and you'll see multiple lensed images, which are labeled by the orbit number of all this stuff around the black hole. And these photon subrings labeled by n, you can see that they converge to a particular curve, which is a theoretical, that is to say, unobservable critical curve, often known as the black hole shadow. But the photon rings, which are the observable signal, are actually distinct from it, and they have a slightly different shape. And one can show that for M87, under some assumptions about the emission source, we think that the n=2 photon ring ought to have the exact shape of an ellipse. So what that means is that if you look at the Fourier transform of the image, which is what we actually measure with an interferometer, you should get from each of these rings a ringing pattern in the visibility. And the key point is that the periodicity of the ringing encodes the diameter of the ring. And these rings get sharper and sharper, and correspondingly, they produce a signal that dominates on longer and longer baselines. And so that led us to propose with Sam Gralla and Dan Moroni an experiment last year, which is something you could do. There's a lot of structure in this photon ring. We think this is a relatively low-hanging fruit. You could have a satellite orbiting in space around the Earth and in the plane perpendicular to the line of sight to M87, measuring this ringing that's caused by the n=2 photon ring at every angle in the orbit. And the periodicity that you would measure in the ringing would tell you the corresponding diameter of the ring at the corresponding angle in the image. And the prediction from GR is that this diameter should be that of an ellipse, which has this functional form, which is plotted here in orange. And we think by putting a satellite in space, you ought to be able to measure this diameter and use that as a test of GR and the Kerr hypothesis. Now, I have very limited time, so let me just give you my big picture takeaway. There's a lot of discussion right now about expanding our black hole imaging capabilities. I think this is super exciting, and it's something we're going to be doing for decades. The current plans involve improving the baseline coverage from Earth, and that's very exciting. It's going to enable us to better resolve the accretion onto the black hole and help us address all these fascinating questions in astrophysics, such as, what is the near horizon magnetic field structure using polarimetric imaging? Can we somehow establish that there's energy extraction from the black hole using the Blandford-Znaik mechanism or some other mechanism? What powers the jet? These are all questions that an experiment like ngEHT, which is earthbound, will help us address, and that's really great. But if we want to probe gravity and fundamental questions, and we want to have very precise probes of gravity in this strong field regime that we can now finally access, and maybe we want to test the Kerr hypothesis with black hole imaging, then I think the place to focus on is this photon ring, which seems like the most promising approach for such tests. There's a lot of people, including at this meeting, that have written about this, but the key takeaway is that this will almost certainly require us going to space. And I think this is a plea to the community to really think about also going into space and how amazing that would be. I think we should really push for that because it'll open a whole new window into black hole physics. And I think we can develop really interesting connections to other fundamental questions. So my big takeaway is photon ring science is doable and worth doing, and let's think about space. And I'll stop here because we're already over time.
Well, thank you very much, Alex, for a very nice talk. And your last comment resonates completely with me. And I think it's one of the things that we very much want to pursue in the fundamental physics working group. And thank you for saving us a little bit of time there. So I do see that the people are still in the other breakout rooms. So we maybe have time for one question, if anybody feels a pressing need to ask a question right now before we all head over. Going, gone. Okay, then that's it for today. Thank you, Alex. Thank you to all of our speakers. Thanks everybody for joining. And thank you also to Sandra for taking care of the recording and organization of this breakout session. And see you all soon. Bye-bye.